Here we're asked to find the direction in which the maximum rate of change occurs for the function f of x comma y at the point 1/2 comma 1/2, and we're asked to give the answer as a unit vector. The gradient of f is going to give us the direction in which the maximum rate of change of the function occurs, which if we have f of x comma y, then the gradient of f is equal to the vectored valued function, where the x component is equal to the partial of f with respect to x, and the y component is equal to the partial of f with respect to y. So we'll first find the gradient, then evaluate it at the point 1/2 comma 1/2, and then we'll find the unit vector in this direction. Then once we do all of this, we'll look at it graphically. So we'll find the gradient of f. So the x component is going to be equal to the partial of f with respect to x, which means we want to differentiate 5x sine of xy with respect to x, treating y as a constant. And notice here we'll have to apply the product rule. So applying the product rule, we have the first function 5x times the derivative of sine xy with respect to x, again treating y as a constant, which would give us cosine of xy times the derivative of xy with respect to x, which would just be y. And then we have plus the second function, which is sine xy, times the derivative of 5x with respect to x, which would be 5. So this would be the x component, and now the y component is going to be the partial of f with respect to y. So now we differentiate 5x sine xy with respect to y, treating x as a constant. So we'd have 5x cosine of xy times the derivative of xy with respect to y, which would be x. Now let's go ahead and simplify this. So here we have 5xy cosine xy plus 5 sine xy, and the y component would be 5x squared cosine of xy. And now we need to evaluate this at the point 1/2 comma 1/2. So we'll substitute 1/2 for x and 1/2 for y. So here we'd have 5 times 1/2 times 1/2, that's 5/4. Cosine of x times y would be 1/2 times 1/2, or 1/4, plus 5 times sine of x times y, again, is 1/2 times 1/2, or 1/4. And for the y component, we have 5 times x squared is 1/2 squared, or 1/4. 5 times 1/4 is 5/4. And we have cosine of x times y, or 1/2 times 1/2, which is 1/4. So this vector here is the vector that points in the direction of the maximum rate of change of f at the point 1/2, 1/2. But we're asked to give the unit vector in the same direction. Before we do this though, let's get decimal approximations for the x and y components. So we want to first make sure we're in radian mode. So we'll press the mode key. Notice how we are in radian mode, so we'll go back to the home screen by pressing second mode. Enter. So the x component is approximately 2.4482. And now we'll approximate the y component, which would be approximately 1.2111. So now we want a unit vector in the same direction. So our unit vector is going to be equal to the gradient of f at the point 1/2, 1/2, divided by the magnitude of the gradient, which would be 2.4482 squared plus 1.2111 squared. Now for our next step, let's get a decimal approximation for the magnitude. So we have approximately 2.7314. And then we'll find the actual x and y components of the unit vector that points in the same direction as a gradient of f. So we have 2.4482 divided by 2.7314. Enter. So approximately 0.8963 for the x component And now for the y component, we have 1.2111 divided by 2.7314. So approximately 0.4434. So this is the unit vector that points in the same direction as the gradient of f, or the unit vector that points in the direction in which the maximum rate of change occurs for the function at the point 1/2, comma 1/2. And let's look at this graphically. It's hard to get a really good graph of the surface because it oscillates so much. But we were given the point 1/2, 1/2, which is this point in the xy plane. This point here is a corresponding point on the surface. So to find the z-coordinate of this point, we'd have to substitute 1/2 for x and 1/2 for y into the function. From here, we were asked to find the direction of the maximum rate of increase of f, and we're asked to express that direction as a unit vector. So what we did is we found the gradient of f, which is this red vector here, which means from this point, if we moved in that direction, we'd move in the direction of the maximum rate of change of f. But because we were asked to express the direction as a unit vector, we normalized the gradient or found a vector in the same direction with a magnitude of 1. I hope you found this helpful.